Hi there, my name is Michael Schröder and I'm a PhD student at TU Wien in Vienna, Austria. This is Grammars for Free, our vision toward grammar inference for ad hoc parsers. Parsers are simply everywhere. Anytime that you split a string, or you slice it, or you extract a substring, you loop over characters, you trim something from the end of a string, or you do any kind of transformation of strings, you are in fact parsing. This is one of the most common activities that pretty much every program performs at one point or another. And we've been studying parsing since the very early days of computer science. Formal language theory is the foundation for an immense amount of theoretical results and practical applications. But apart from some very special applications like compilers or some protocol implementations, we usually don't think about formal languages or parsing theory, even when we are parsing something. The vast majority of parsing code, like all the examples on this slide, is completely ad hoc. Many minor programming tasks involving strings, even though they are parsing, barely register as parsing. Take another example, this piece of Python code. It doesn't use any particular parsing techniques or frameworks, it's just a few ordinary functions manipulating a string and transforming some values. If the variable s here is the string 1, 2, 3, then you get out a list of integers 1, 2, 3. This is a typical ad hoc parser. But what happens if s is the empty string? Can you tell from just looking at the code? Well, it turns out that the empty string actually crashes this program. And what about this weird looking string? Is that an acceptable input? Yes, it turns out that, perhaps surprisingly, this is indeed a valid input string for this parser. So you could try out all different kinds of test inputs until you're satisfied that you know what the parser does. Although it could actually be quite difficult to write proper unit tests because ad hoc parsers like this tend to be deeply entangled with application logic and they don't really appear as easily isolatable units. So if you really want to find out what a parser like this does, you have to look up what each of its sub-expressions does. And the exact specifications of even standard functions like split or a built-in string to integer conversion, they are often more complex than one would initially assume. And they often differ in some details and edge cases between languages or even between different versions of the same language. So it can actually be quite tricky to figure out what such a deceptively simple-looking ad hoc parser actually does. Unless, of course, you know the parser's grammar. Here is the complete grammar for this parser, in both textual and graphical forms. The grammar is a finite formal description of all the accepted inputs of the parser and, by extension, of all the non-accepted inputs. Without having to know anything about the particular implementation details of the parser, it allows you to see, for example, that the empty string is not actually part of the language and therefore cannot be a valid input for this piece of code. Grammars can be very helpful for comprehending your program, and they make for great documentation. A formal grammar provides you with a high-level data-centric perspective. It allows you to abstract away implementation details and enables you to grasp the input language without being distracted by mechanics. They come in a variety of different notations, each suitable for a different occasion. Graphical representations, like we saw earlier, can be particularly helpful. And because grammars are a generating device, they allow us to generate concrete examples of test inputs for our programs. This makes them really useful for fuzzing. Because without any prior knowledge of the possible input space, it's usually not easy to generate good fuzz inputs. In order to penetrate into deep program states, test inputs usually need to pass various syntactic checks, such as are often performed by ad hoc parsers that are intermingled with application logic. And grammar-based fuzzing is obviously much more efficient here, because it allows you to generate known valid inputs based on the input grammar, and those can cover a lot more code paths. Grammars also allow you to reason about language-theoretic properties, such as computability bounds, whether it's possible that certain inputs may cause your parser to never terminate, for example. The language-theoretic security community has some very strong opinions on how input languages should generally be as minimally powerful as possible, which you could determine on the basis of their grammar. And they have drawn a direct line between ad hoc parsing code and security vulnerabilities, especially internet-related ones. So there's all these great benefits to having an explicit grammar for your parsing code. Now, the problem, of course, is that nobody ever bothers to write down a grammar like this. Hence all of these ad hoc parsers everywhere. In this way, grammars share the same fate as most other forms of specification. They are just too heavy-handed. It takes too much effort to write them down, and you also still have to make sure that the grammar you write down actually reflects what the parser does. But there is a particularly lightweight form of specification that is very successful and that we can draw inspiration from. and that is types. Grammars are similar to types in the sense that a parser without a grammar is very much like a function without a type signature. It's still going to work, but you might not be sure about what it does, and you certainly won't have any compile time guarantees about it. But types have one significant advantage over grammars. Most type systems offer some form of type inference. This allows programmers to generally omit type annotations because they can be automatically recovered from the surrounding program context. And then various kinds of tooling, like IDEs, can take advantage of these inferred types. Well, what if that was possible for grammars as well? What if we could infer grammars just like we can infer types? This is our vision. Let me now walk you through why and how we think that automatic grammar inference for ad hoc parsers could actually be done. So a language is a possibly infinite set of sentences over some alphabet. That's the formal definition. We can define a language in a very abstract mathematical way, as in this example here, but usually we want to define a language via a grammar, which is a finite description of the language in the form of production rules, involving an alphabet and some non-terminal symbols. Another way to define a language is via a machine, a program that recognizes words by moving through a finite number of internal states and finally arriving at some halting configuration if and only if the word is part of the language. So basically a parser. Any language is situated somewhere along the famous Chomsky hierarchy, which tells us how complex a machine that recognizes this language would have to be, or what kinds of production rules we would need in a grammar describing the language. This language here is context-free, for example. So what about a piece of ad hoc parsing code like this? So clearly that is a machine representation of a language. It's a program. And it's a program that takes some input, and depending on the input, it either halts in some favorable state, or it never halts, or it produces an error, or something else. So it should also be possible to have a grammar representation of this machine's input language, right? Well, unfortunately, this program is written in a general purpose programming language, which means that this language recognizing machine that the program represents is basically a Turing machine, able to recognize any language in this highest class of recursively enumerable languages. So on the surface, this makes it rather impossible to actually figure out which language this parser exactly recognizes, or to construct an equivalent grammar representation in any automated fashion. However, if we look at just those core parts of the program that are actually concerned with parsing, we will find that in isolation, their control flow and their complexity will closely match that of a lesser machine that is exactly the recognizer for the parsed language. Now, any real-world parser or any real-world program will of course do much more than just recognize a language. It will allocate memory, it will throw exceptions, it will perform any kind of unrelated side effects and so on. But at its core, a parser is essentially a recognizing machine that will not significantly exceed the power level of the language it is parsing. A parser, particularly an ad hoc parser, is a simpler machine embedded within the larger machine that is modeled by the general purpose programming language that the whole program is written in. This is the intuition behind our approach. In our vision for an end-to-end grammar inference system, we start out with ad hoc parsing code in some Turing-complete source language, for example Python. In the first step, we simplify the source language into an intermediate representation that is essentially a domain-specific language for parsing. In this transformation, we remove syntactic sugar, we make control flow explicit, and we throw away all parts of the source that are not related to parsing. In order to be able to do this, we need precise specifications of the source language's string processing functions so that we can translate them into equivalent operations in our intermediate language. And of course, for each possible source language, we will need a separate set of these specifications, but they only have to be defined once. From our intermediate representation, we then hope to infer a language model. Currently, we are building our approach on a refinement type system, which we use to generate precise constraints over the program's input string, and those constraints, with the help of an SMT solver, are then resolved into this language model. The language model is not yet itself the final grammar, but a more abstract representation, from which we can then in turn generate the desired textual or visual grammar representations. And for interactive applications, we can also use this language model to synthesize parsing code again. It is important that through all the steps of this process, we always preserve rich source location information so that in the resulting grammars we can precisely trace productions back to the originating code. Now let's look at some of the exciting new possibilities that an end-to-end grammar inference system like the one I just described would enable. First off, an inferred grammar is not just a static piece of documentation, it can be interactive in a way that a handwritten grammar cannot. An inferred grammar is always up to date, and it is closely linked to the underlying source code from which it was inferred. So you can imagine, for example, an IDE plugin that shows you the implicit input grammar whenever you hover over a function definition. And because the inferred grammar is so closely connected to the code, you can dig deeper into individual production rules on non-terminals to find out where they originate. Another new possibility enabled by grammar inference is bi-directional parser synthesis, which is the combination of inference with existing parser generation techniques. In the most basic case, starting from a complete existing parser implementation, we can use the inferred grammar to perform semantic program transformations, generating different implementations of a parser based on the same grammar. So you could refactor a parser according to certain criteria like performance or code style, while for sure preserving the grammar of the parser. A more advanced application would be program sketching. Here, we start out with an incomplete program, a sketch. We use grammar inference to get an initial grammar from the sketch. The user can then manipulate this grammar into a more refined grammar that more closely matches what they have in mind. And from this refined grammar, a refined program that fills out the sketch is then synthesized. Of course, we can loop this back to let the user again manipulate the grammar of this refined sketch and then synthesize another even more refined program and so on. If this sketch synth loop can be sufficiently shortened, it is effectively a direct manipulation bi-directional programming system for parsers. Some especially interesting applications arise in the areas of mining and learning. A grammar is basically an equivalence class over concrete parser implementations. So it allows us to group together different implementations with similar semantics. This can allow us to detect code clones of ad hoc parsers, and it also enables us to build a type of grammar-based code search. A user can query for certain production rules or grammar patterns, and the search engine can return specific instances of implementations of these grammar rules. We can also watch how the mined grammars change over time and thereby learn how these implicit input specifications that the grammars represent evolve. This enables us to do grammar-aware semantic change tracking. Imagine a build bot that augments the code review process with current and historical grammar information so that a programmer is alerted whenever a code change introduces a perhaps unexpected change in an input grammar. We are hoping to realize everything that I have described so far, at least in prototypical form, and to this end we are working on a number of related projects. First, we are currently conducting a mining study of ad hoc parsers in order to collect typical examples and common coding patterns. This is ongoing work. If after this talk you now happen to recognize some ad hoc parsers in your own code, please don't hesitate to send them to us. We are continuously looking for specimens. The main part of our work, of course, is the core grammar inference algorithm itself. We are currently building this on top of a refinement type system, as I've mentioned, and we hope to be able to publish some preliminary results in this area soon. To ensure the validity of what we are doing, we want to supply soundness proofs for the transformations involved in the simplification step and for our inference. And we plan on evaluating the effectiveness and the performance of our system on a corpus of curated ad hoc parser samples. Once we have a functional end-to-end system in place, we plan on conducting a large-scale mining study of inferred grammars, both to demonstrate the practicability of our system and to find out what kinds of hidden implicit input grammars lurk out there in the wild. Finally, we also plan on conducting a number of user studies on various aspects of grammar comprehension and usability to determine the benefits and drawbacks of different kinds of grammar representations and how inferred grammars can be most effectively employed during the software development process. So, thank you very much for watching this presentation. We are very excited about the prospects of automated grammar inference, and we invite the community to collaborate with us to realize our vision of grammars for free.